right, let's look at one last problem in the section on volume rotation. This problem says the following. Suppose you make napkin rings by drilling holes with different diameters through two wooden balls, which also have different diameters. You discover that both napkin rings have the same height, which we're going to call 3h, as shown in the figure below. So we're letting A be equal to 3. This problem has two parts. In part A, it wants to know which ring has more wood in it. So I suggest we come back and answer part A in just a second. I'm going to look at part B first. Part B says, use cylindrical shells to compute the volume of each one of these napkin rings with a height of 3h, and then express it in terms of h. So what I'm going to do is I'm going to graph sort of arbitrarily either one of these, it doesn't matter which one, in the following way. I'm actually only going to graph, again, I'm going to make use of symmetry here. So I only want to graph the top half of one of these napkin rings. So when I graph it, actually, I want to try to graph this kind of as round as I can. Okay, that's supposed to be a circle, but I don't want to graph the whole thing. So what I'm going to do is just graph. So if we were to drill our hole right here, let me make this a little bit darker. You can see it so over here and over here. So here are these regions, so you can nicely see. All right, so this is the solid region that we are going to rotate. All right, and so this will kind of have this kind of a look to it. All right. So what I'm going to do is I'm going to call this the small radius and the big radius. I'm going to call it little r. We'll call this guy big R. So this is the two radii that's going to form that shape for us. And also, let me quickly scroll up here. So what I decided to do, again, this corresponds to the picture that I just drew here. So it doesn't matter. For the first ball, we can call it small r1, big R1. And for the second ball, small r2 and big R2. But you see, for both of them, the height is the same, 3h. So if I'm only considering this top half of the circle, then you're going to see that we're going to have 3h over 2 is going to be our y value. This is going to be my y value up here. All right. All right. So this is going to be 3h, this y value right here. Let me do this in a different color. So our y value up here is 3h over 2. All right, so I want to come up with the equation for this circle right here. So equation of this circle, again, we know x squared plus y squared is equal to the radius squared. So this will be big R squared. And you can solve for either x or y here. We can say y squared is equal to r squared minus x squared, or specifically y is equal to the square root of big R squared minus x squared. So now we have a function that we can actually go ahead and rotate. So according to the shell method, we're going to have here the volume is equal to, and again, I'm only graphing half of this ball, so I have to multiply my volume by 2. So 2 pi times the integral of point radius here is just going to be x, because I'm simply rotating around the y-axis. And then my function, top minus bottom, is going to be the square root of r squared minus x squared dx. And then the final thing are the bounds. You see the domain for this region. Again, we're integrating from here to here. So the domain simply is from little r to big R. Right? And again, the reason that I'm multiplying my integral by 2 is because I've only graphed the top half. I'm using symmetry here to just make the integral a little bit easier. All right, so let's see if we can evaluate this integral. I can, using u substitution. And so let's pick a different color here so this is kind of clear what we're doing. So by u substitution, I'm going to let u be equal to r squared minus x squared. So then the differential du is equal to minus 2x dx. We do have an x dx in our problem, so if we can just take that minus 2 to the other side. So divide both sides by minus 2, I get x dx. So again, just to be clear, all of this stuff here is my u, and then the x dx is going to become negative 1/2 du. So here's what we have. 4 pi times the integral of the square root of u times negative 1/2 du. In other words, if we can factor out that negative 1/2, we're going to have negative 2 pi times the integral of u to the power 1/2 du, which is equal to minus 2 pi. The integral of u to the power 1/2 is u to the power 3/2. You can either divide by 3/2 or immediately multiply by 2/3. And then final simplification here before we back substitute. This is negative 4/3 pi times u squared. So let's go ahead and back substitute. The u is equal to our big R squared minus x squared raised to the power 3/2. And we want to evaluate this integral on the integral from little r to big R. All right, so let's plug in top minus plug in bottom. So this is equal to negative 4/3 pi. All right, if we plug in the top, we're going to get big R squared minus big R squared to the power 3/2 minus, plug in the bottom, I get big R squared minus little r squared raised to the power 3/2. Right? So you see that big R squared minus big R squared is equal to 0. So I get negative 4/3 pi times 0 minus big R squared minus little r squared raised to the power 3/2. Right? And so finally this is equal to negative 4/3 pi times negative big R squared minus little r squared to the power 3/2. So this will just be 4/3 pi big R squared minus little r squared to the power 3/2. All right, so this is what I get my integral to be equal to. Let's go ahead and copy this over. I'm not done with the problem. Let's go ahead and put up here what we got. So we got the volume to be equal to 4/3 big R squared minus little r squared raised to the power 3/2. So I would really like to come up with some expression for the big R squared minus little r squared. And again, what I'm going to do is, again, let's look at specifically this triangle that formed right here, where we had big R was the hypotenuse, and then we had little r, and we had this height right here. So if I graphed, I'm just going to redraw this little triangle for you. So we had little r, and then we had this height, and then we had our hypotenuse. So this was little r, this was big R, and again this height was 3h/2. So by Pythagorean theorem, we can see that big R squared minus little r squared is going to be equal to 3h/2 quantity squared. So if we replace in this equation the big R squared minus little r squared, we're going to get that the volume is equal to 4/3 times 3h/2 quantity squared, everything raised to the power 3/2. All right, so some simplification here says we can cancel out those 2's. And this is then equal to 4/3 times 3h over 2 quantity cubed. So this will be equal to, let's see, 4/3 times, all right, if I cube everything, this will be 27 times h cubed over 8. And finally, this is equal to just 9 over 2 h cubed. Now keep in mind, this is the volume. So the volume for each one of those napkin rings is going to be 9 over 2 h cubed. This tells us two things, all right? Number one, the volumes are equal, all right? And number two, the volume is independent of little r1, big R1, little r2, or big R2. Right? So we were able to calculate the volume for each, and we can see that it is not dependent on any one of those radii. So I'm going to come back here, and now we can actually answer confidently part A. It says, which ring has more wood in it? I'm going to say answer C here. The amount of wood in each napkin ring is the same, regardless of the size of the sphere that is used.